The base 2 number system is also commonly called binary, the binary system. And it consists of just 2 digits, starting with 0 and then going to 1. So those are the only 2 digits we have in base 2. So every number expressed in base 2 is going to be a string of zeros and ones. And it's a natural for computer science, because as you probably learned, computers are just a massive box of on and off switches, and so if a switch is turned on, we can represent that with a 1. If it's turned off, we can represent it with a 0. And so it's very useful to represent the big sequences of ons and offs with ones and zeros. And now then, so how do you count in the binary system? Well, 0 and 1, we don't have a digit for the number 2, so we have to create a second place. And it looks like 10. Okay, it's not truly 10 though. It's 2 in base 2 is 1, 0. So it looks like 10, but probably be better off not calling it 10. You should call that 2. And so now I can add 1 to this and get 1, 1. I know that looks like 11, but it's not. It's 1, 1 in base 2. And I've run out of digits again, so now I have to create a third place. 1, 0, 0. So now it jumps to what appears to be 100. So I'll keep counting here. So 1, 0, 1, I'm sorry, 1, 0, 0. 5 will be 1, 0, 1. 6 is 1, 1, 0. 7 is 1, 1, 1. 8 jumps to a new place, 1, 0, 0, 0. And then 9 is 1, 0, 0, 1. 10, 1, 0, 1, 0. 11, 1, 0, 1, 1. And 12 is 1, 1, 0, 0. So anyway, hopefully you've got the hang of counting in base 2. Kind of our job here is to figure out a nice way to translate these base 2 numbers into base 10 and backwards, back and forth. And so I've got kind of a systematic way that I want to show you for being able to translate from one system to the other. And but it really means that we have to understand that place value system that I mentioned in the first video. And in the 2 system, we go by powers of 2. For example, 11, let's look at 11 down here. So 1, 0, 1, 1, base 2. I'm going to, most of the time I'll use a subscript to indicate the base when we're talking about base 2. 1, 0, 1, 1 is going to be, let me see, the place values go 1, 2, 4, and 8. We're building up in powers of 2. So this is 2 to the 0, 2 to the first, 2 to the second, 2 to the third. So this is equal to 1 times 2 to the third plus 0 times 2 squared plus 1 times 2 to the first plus 1. 1 times 2 to the 0 is just plain old 1. And so 1, 0, 1, 1 ends up being this sum here. Now here you can see the 1, 0, 1, 1. But in order to translate this into base 10, I've got to go 1 times 2 to the third. So that's 1 times 8. 0 times 4. 1 times 2. And 1. So 8 plus 2 plus 1, of course, is our common number 11. And I see I kind of unfortunately picked a number that looks like a base 2 number, but by this I mean our ordinary 11 in base 10. All right. All right, well, I'm going to erase the board and show you some examples of how we can convert from a binary number to a decimal number. I created a chart for 8-digit numbers. Is that right? 1, 2, 3, 4, 5, 6, 7, 8. 8-digit number. And the heading up here are powers of 2. So this is 2 to the first power, 2 to the second, I'm sorry, 2 to the 0, 2 to the first, 2 to the second, 2 to the third, 2 times 2 times 2 is 8, times 2 is 16, 2 to the fourth, times 2 is 32, 2 to the fifth, and so on. And so 128 is 2 raised to the 7th power. Now, if I recall right, I'm not a computer scientist, but I believe 8 bits could be represented as an 8-digit binary number. Represents 1 byte of information. So 1 byte of information is could be coded as a number between 0 and 255. So I'll elaborate on that in a minute a little bit better. But anyway, I came up with this chart, and which I think is kind of a simple way to convert numbers from the binary system over to the decimal base 10 system. So let's start off with a small one, 110 in base 2. 110 means it's going to be 4 plus 2. So we have 4 plus 2. So 110 base 2 is 4 plus 2, which is 6. There you go. And so you think 1 times 4, 1 times 2. Very simple. Let's try another one. How about 1001 base 2? Now I think you should try this. So let me encourage you to pause the video after each time I put a problem up and see if you can figure it out on your own. If you want to learn this quickly and well, you should try to work along with me on this. So pause it for a second. See if you can figure out what 1001 base 2 equals to. Alright, well, I'm going to fill it in. Let me I'll draw a line across here so we can separate it well. So 1001 base 2 will be 8 plus 1, or our common number 9. Alright, so let's try a couple more of these, and again, I would pause each time, see if you can figure it out, and if you do that rather than just watch me, then this will sink in pretty fast, I think. So here comes the number, 11001 base 2. Okay, so basically I have a five-digit number. So I start over here, and we've got 11001. So I have 16 plus 8 plus 0 and 0, and then plus 1. So I'm going to leave out the zeros there, but 16 plus 8 plus 1, which would be 25. So 11001 base 2 will be the number 25. All right. Now, if you had a printout of a long strings of zeros and ones, it's going to get kind of eye glazing after a while, and but it's I think it's typical in computer science to separate those long strings of zeros and ones into smaller sections where we can interpret it in base 8 or 16. So I'll elaborate on that as we move on. All right, let's try 2 more. So here's a full 8-digit number. 101101 10. Okay, base 2. So did I get 8 digits? 1011011. I have no idea what that is, and but why don't you try it? Fill in your ones and zeros and then add them up and see if you can get my answer. All right, so 8 digits, and this covers 8 digits. So I'll start with a 1, 0, 1, 1, 0, 1, 1, 0. And so this number will be 128 plus 32 plus 16 plus 4 plus 2. And so that adds up to, I don't know what that adds up to. Let's see, 160, 176, 180, 182. So if I did that right, that should be 182 in base 10. There you go. Now let's try, what's the largest number with a byte of information? Okay, 8 bits equals 1 byte. So the largest possible number you can come up with 8 places is nothing but ones. 1, 1, 1, 1, 1, 1, 1, 1. So add that up and it equals to 255. All right, I just knew that. Okay, and here's how I knew that. Because if I go to a 9th place value, a 9th place value will be 2 to the 9th power, which is 2 times 128. That's 256. And so just before you get to the 9th place value, you've got nothing but ones. So subtract 1 from 256 and you get 255. So anyway, now it's I think it's typical, and your computer professors can elaborate on this better than I can, but I believe it's very typical to represent color on a computer screen in 24-bit color. 24-bit color means that the primary colors, red, green, and blue, are separated into 8 bits. And so numerically, when your computer stores a pixel as a graphic image, as its own little tiny graphic image, the little pixel has a string of 24 ones and zeros. The computer must store that into memory for just that single pixel. Now imagine all the pixels on a computer screen. It's in the many thousands, probably into the millions by now. And so each little pixel is stored with 24 bits of information. I think this is how it works. And if I'm wrong, then computer faculty will fix it for me. But each color gets 8 bits, which means there's a string of numbers like this for red, and for green, and for blue. And so each color has 256 shades. And so if red is represented as nothing but zeros, then there's no red color in that pixel. And if the value of red is just 1, that means there's just a slight hint of red in that pixel. But if you go up to 255, which is our largest number, then that means full red coloring for that pixel. Anyway, so when you look at this, then that means a computer screen which has 24-bit color, if I multiply 256 times 256 times 256, or if you raise 2 to the 24th power, it would be the same thing. That means there are 16,777,216 possible different colors that can be represented on a computer screen. I'm not sure the human eye can actually detect that many different shades. It seemed like I recall the number 40 million. So the human eye might be able to detect some shade is not represented on such a computer screen. I don't know, but it's for most of us it works pretty well, doesn't it? Okay. All right. So I've introduced converting a base 2 number over to base 10, but only up to 1 byte of information. Let me just do one longer problem here. And so I'm going to erase the board and just do one really big long one. Here's a 14-digit number I put up here. And see if we can convert that to base 10. So this will be a good challenge for you. So again, I would pause it, see if you can figure that out. And then I'll show you how I do it. Now, I didn't keep that chart up there. I took it off because I didn't want to go out to 14 places. So, but 14 places means this first digit is in the 2 to the 13th power. So, count over with me. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So this would be 2 to the 13th. I don't recall what that is. This is the 12th place value, and it's a 0. Then here's the 11th place value, so this is 2 to the 11th, 2 to the 10th, 2 to the 9th, 8, 7, 6, 2 to the 6th, 5, 2 to the 4th, 3, 2 squared, 2 to the 1st, and 2 to the 0 is 1. So we would have to add up all those numbers, and 2 raised to the 13th is 8,192, 8192, plus 2 raised to the 11th, I think is 2048, 2048, 2 to the 10th. By the way, 2 to the 10th is kind of a special number. It's 1,024. Because it's close to our 1,000, our common value 1,000, you see 2 to the 10th show up all over the place. So a kilobyte is 2 to the 10th bytes, or 1,024 bytes. A megabyte is 1,024 kilobytes. And it works that way. So every time you go from kilo to mega to, what's after mega? Gigabytes. You're stepping it up by a power of 2 to the 10th, or 1,024. So anyway, that shows up quite a bit. So where am I up to here? 2,048 plus 1,024, 512, 2 to the 6th, I recall, is 64, and then 2 to the 4th is 16, 2 squared is 4, plus 2 plus 1. So, hope I got that right. I believe I do. Okay. All right. So let's see. 8192 plus 2048 plus 1024 plus 512 plus 64 plus 16 plus 4 plus 2 plus 1 is 11,863. All right, so which, when you think about it, this list looks humongous, but it's only our number, 11,863. So it takes a lot of digits to represent a very large number in base 10. All right, well, I'm going to erase the board again, and now we'll talk about converting from the base 10 system over to base 2. I think converting from base 10 over to base 2 is a little harder, or a little more work, I should say. So let's start off kind of small here. What is 14 in base 2? All right, well, 14 in base 2, I can subtract. 14 is less than 16, so I'll subtract 8. I'll put a 1 there because I subtracted 8. 14 minus 8 is 6. I can subtract 4 from this, so I'll put a 1 there. The answer is 2. I can subtract 2. And now the remainder is 0, so I cannot subtract 1. So 14 would be 1110. 1110 base 2. And so that's how you could do this. Now, I think this will require a little more calculator work when we get to base 8 and base 16, but it's not too bad in base 2. Let's try a couple more here. And again, pause the video and see if you can figure these out. So let's try the number 23 and see how that goes. Now, for 23, my largest number I can subtract and get a positive result would be 16. So I'll subtract 16 from 23, and that gives me 7. Now I cannot subtract 8, because 8 is larger than 7, so I'm going to put a 0 in the 8 position. But I can subtract 4, and that gives me a 3. I can subtract our next number, 2. And when I do so, the remainder is 1. I can subtract 1 and get down to my, I don't know if you can see quite this well in this video, but I got down to a remainder of 0 by this subtraction. So I don't know if this occurred to you, but the process of subtracting is a division process like this. It's kind of a division type process. Anyway, 23, a base 10 number, would be 10111 base 2. So in binary it's 10111. I would resist calling this 10,111. Right, it's a base 2 number, not a base 10 number, so I would just call it 10111. Alright, let's try a little bigger number. 105. Okay, let's see if you can get that one. So try this. You know, pause the video and try that and see if you can figure out what 105 translates to in base 2. So our largest number we can subtract from this list would be 64. And so 105 minus 64 will be 41. From 41 I can subtract 32. And it gives me, what, a 9? And then from 9 I cannot subtract 16. But we can subtract 8. And the remainder is 1, so I'm just going to fill in 2 zeros and then a 1. And because the only thing left I can subtract is 1. So 105 translates to 1101001 base 2. There we go. So let's do another one of these, and kind of quickly I'll do a kind of a full 8-bit number. Okay, that could be represented by a byte of information. And so let's see, let's go with 175 and see what happens. So again, you try this, pause the video and see what you get. Well, here we go. We can subtract 128 from 175, and we get, I believe, 47. Yeah, 47. Now I can't subtract 64, so that's a 0. I can subtract 32, and I'll get 15. Now, I can't subtract 16, so I put a 0 in the 16's place. But 15, after a while, you begin to recognize 15 is 1 less than 16. And so its binary number is 1111. But you can do that piecemeal. You know, 15 minus 8 is 7. 7 minus 4 is 3. 3 minus 2 is 1. And then 1 minus 1 is 0. So you can continue to work through that if you like. And 175 then is going to be 10101111 base 2. And there you have it. Alright, so let me erase the board. We'll do one much longer problem just to show you how you could do a longer problem if you had to. Well, here's a number that's going to be pretty big in the binary system. 19,271 in base 10. And where in the world do you start with this? Okay, well, you could make up a very wide chart like I did before if you wanted to. There's a number of ways you could approach this depending on how well you recognize powers of 2. And I think I'll do it this way. We have, let's see, power. Let me write a column here. Power 2 to that power. So 2 to the first is 1, 2 squared is 2, 2 cubed is 8, 16, 32, 64, and I'm just going down the line here, powers of 2, so I can get everything out there. 256, another power, column, and 2 to that power. So 2 to the 9th power will be twice this, 512. 2 to the 10th is 1024. And to me, I like 2 to the 10th because I remember it. It's, like I mentioned before, it's related to how we use the word kilo or mega or giga in computer language. You know, a kilobyte would be 1024 bytes, for example. So that's kind of a nice number to know if you have to convert large numbers. Anyway, 11th power will be 2048. 12th would be 4096. 13th would be 8192. And 14th power is 16,384. I think that's as high as I need to go, because 19,271 is a little bit larger than 16,384, but the next number up is going to be around 32,000 something, and much larger than this. So it looks like we need a 14th power. So let's see, how can we do that? Well, let me mark that one. Okay, so I'm going to take 19,271 and subtract 16,384. I get 2,887. So 2,887 is smaller than these two numbers. However, I can subtract 2,048. So I'll take the number on my calculator, 2887, and subtract 2,048. I get 839. So that's larger than 839, but not 512. I can subtract 512. So 839 minus 512 is 327. I can subtract 256 from 327, so I'll subtract 256. I get 71. 71 is smaller than 128, but larger than 64, so I'll subtract 64 and get 7. So 7 is smaller than these three numbers, but I can subtract. I see a mistake. You probably spotted it early. I just spotted that mistake. That should have been a 4, shouldn't it? 2 squared is 4. Alright, so from 7 I can subtract 4 and 2, and you know, I should have put 0 in here. 2 to the 0 is 1, so I can also subtract 1. Alright, so let's see what we got here. This should be equal to, now start from high to low. So it's going to be 1, 0, 0, 1, 0, 1, 1, 0, 1, 0, 0, 0, 1, 1, 1. So this should be a 15-digit number because I'm going from a power of 0, which is the units place, up to a power of 14. So I'm going to mark that as base 2. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Alright, so just make sure you don't do it backwards. The highest power goes on the left, so I have 2 to the 14th, plus 2 to the 11th, plus 2 to the 9th, 2 to the 8th, 2 to the 6th, 5, 4, 3, 2 to the 4th, 2 to the 2nd, 2 to the 1st, and 1. So anyway, that's yeah, that's kind of tedious, isn't it? Okay, but that's how we could look at a somewhat larger number systematically, I believe. Okay, and I think your success will be based upon how well you organize your work. Okay, is going to be part of that success. Well, we have converted from base 2 to base 10, and now we've looked at converting from base 10 over to base 2. Our next video, we're going to look at the base 8 system, which is called the octal system.